Hi everyone, this will be our video on the Solubility Equilibria tutorial. Now for the first question here, this is an MCQ question. So you are given that the solubility product, basically your KSP of zinc carbonate and your silver carbonate is given in the table below. So the scenario here is you have a solution containing 0.02 moles per dm cube of zinc nitrate and 0.02 moles per dm cube of silver nitrate at 25 degrees Celsius. So you are told that the zinc and the silver ions can be separated by adding solid sodium carbonate slowly. So which of the following statement is correct? Now, based on the four statements given to you, the first one, option A, is incorrect. Okay, your silver carbonate will precipitate before your zinc carbonate. This is incorrect. Now, how do we know that this is incorrect? We can actually do some calculations to verify this. So the concept here is this. For precipitation to occur, your IP, your ionic product, must be greater than your KSP. That precipitation will occur. So the salt that requires a lower minimum concentration of your carbonate will be the one to precipitate first. Now, based on that, so you see, let's take a look on this side first for the zinc carbonate. So the KSP of zinc carbonate, if you were to write out the expression, it will be the concentration of a zinc 2 plus multiplied by the concentration of your carbonate ion. So now, working backwards, to find the minimum concentration for your zinc carbonate, right? The minimum concentration of the carbonate ions here. So what you can do here is you can use the KSP value divided by 0.02. Now this 0.02 is because I started off with zinc nitrate. Now please recall, all nitrates are fully soluble in water. So your 0.02 moles of your zinc nitrate will fully dissolve to give you 0.02 moles per dm cube of your zinc ion here. So do that carefully. The concentration of your carbonate for your zinc, for the zinc carbonate here, right, will be 7.3 times 10 minus 9. Similarly, the same idea goes for your silver carbonate here. So if you do everything correctly, you will realize that the value for your silver carbonate here will be 2.115 times 10 minus 8 moles per dm cube. So compare the two values. Do you notice the magnitude here for your zinc, right, is minus 9, but the magnitude here for your carbonate is minus 8. So this is a smaller number. So because it's a smaller number, your zinc carbonate will be the one to precipitate first and not your silver carbonate. Hence, option A is incorrect. Now, let's move on to option B then. Now, in option B, you're told that the solubility of your silver carbonate in water is 2.04 times 10 minus 4. Now, this again is incorrect. We can again do a calculation to verify this. So, I do not know what is the solubility, so I can let it be x mole per dm cube. Now, for the dissolution or for the dissolving of your silver carbonate, you can write it as silver carbonate. Okay, please take note. This is, remember, all carbonates are insoluble, right? Except for your spar carbonate, your sodium, potassium, and ammonium carbonate. So for this case, it will be sparingly soluble. We will use a reversible arrow to represent it. So see, your silver carbonate will dissolve and dissociate, partially dissolve to give you 2 Ag plus and 1 times CO3 2 minus. So the modified ice table here, you can just focus on the equilibrium concentration. So since I let the solubility be x, right? So it's a 2:1 ratio, that's why it's 2x and x for your carbonate here. Now, so the KSP value wise, so what you can do is you can write the KSP expression to, and in terms of unknown algebra. So do it carefully, you should get 4x to the power of 3. So now, the solubility wise will be x. So what we're going to do here is we want to find out the x value, right? So you're given that, in the previous table, you're given that your table, your KSP value is 8.46 times 10 minus 12. So what you have to do here is go backwards, you divide by 4, then you cube root the answer. So the solubility of your silver carbonate should be 1.284 times 10 minus 4 moles per dm cube. So see, it's quite different. It's quite a huge value away from the 2.04 that is given. Hence, option B is incorrect. Now, move on to option C now. Now, in option C, at any point in time, only one compound, either your silver carbonate or your zinc carbonate, can be precipitated. Now, this is incorrect. Why? Concept here. As long as your ionic product is greater than the KSP, the salt will start to precipitate. So, be it your silver or zinc carbonate, as long as their values, the IP value is greater than their individual KSP value, they will start to precipitate. So, from option A, right, we have actually calculated the minimum carbonate concentration for your silver carbonate will be 2.115 times 10 minus 8, and that for your zinc, right, will be 7.3 times 10 minus 9. So you see, because of that, right, both of them will precipitate concurrently. The only difference now is your zinc carbonate will precipitate out more, okay, since most of it has already precipitated. So in other words, both will be precipitating at the same time, so not one by one. All right. Now, last option, option D is the correct option here. Okay, the more soluble compound will first start to precipitate. The concentration, and when it starts to precipitate, right, the concentration of ions is 2.12 times 10 minus 8. So actually this one is from the option A. If you do the calculation, you realize that this value here is 2.115 times 10 minus 8. So to 3SF answer is actually 2.12. All right. Okay, moving on. Now in question 2a, you're given 0.5 dm cube of this concentration of calcium chloride and 0.25 dm cube of this concentration of sodium sulfate are mixed together. Now you're given that the KSP value of your calcium sulfate is this value. Predict whether a precipitate will form or not. So if you want to predict whether a precipitate will form or not, again remember, as long as your IP value is equals or greater than your KSP value, your PPT will form. Okay, so we have to verify that. Now to do so, let's calculate our concentration of your calcium 2 plus first. So the concentration of your calcium 2 plus will be 0.140, this is the concentration, multiplied by the volume, so this one comes from your calcium chloride solution, divided by, now you're mixing two solutions, so the total volume will now be 0.5 dm cube plus 0.25 dm cube. This will be the new volume. So because of that, the new concentration of your calcium 2 plus after you mix everything together will be 9.33 times 10 minus 3 moles per dm cube. Now, again, the same idea, you can use that to calculate for your sulfate. So use the concentration of your sodium sulfate, multiply by the volume you use, divided by the new total volume when you mix everything together. So the concentration of your sulfate in the mixture will now be 6.667 times 10 minus 2 moles per dm cube. Now, this is your equation to show the dissolving of your calcium sulfate, the partial dissolving, since this is a sparingly soluble salt. So from there, you can calculate the IP. The IP will just be, the IP expression is actually very similar to your KSP expression. So you'll be multiplying the concentration of the so-called the ions, the products here. So when you multiply these two values together, what you get here is 6.222 times 10 minus 4. So if you round up to 3SF answer, it will be 6.22 times 10 minus 4 mole square dm minus 6. Now this value is greater than the KSP, right? You see the KSP value here. You see it's greater than the KSP value given to you here. So because it's greater, hence it will start to precipitate. Okay. Now move on to question 2b. You're given 0.1 mole per dm cube of silver nitrate slowly added to a 1 dm cube solution containing 0.1 mole per dm cube chloride solution and 0.1 mole per dm cube of iodide solution. Show that the AgI precipitate before your AgCl, and you're given the KSP of your AgCl as well as your AgI accordingly. So for this again, now the concept here is this. For precipitation to occur, your IP must be greater than your KSP, right? So because of that, I want to have this in mind. So I need to write out the equation to show the dissolving of my silver chloride first for me to be able to work out my IP value. So this is the equation. Now, so based on the equation, your KSP value, your KSP, right, will be the concentration of your silver multiplied by 0.01. Now, why I multiply by 0.01? Because I'm adding it to this solution, your chloride solution. So by this value, so in order for precipitation to occur, this must be greater than your KSP value, right? That's why I say greater than this. So work out your maths carefully, do your manipulation carefully. Your silver, your Ag plus, right, the concentration of silver plus must be greater than 1.2 times 10 minus 8 mole per dm cube. Same idea, you can apply this same idea to your silver iodide. So if you work it out carefully, so silver iodide will be the concentration of silver multiplied by 0.01. This time around, the 0.01 is because of the 0.01 mole per dm cube of I minus that you added to. So this value should be greater than 8.5 times 10 minus 17, which is the value given to you here. So manipulate carefully, you realize that your silver plus for your AgI, right, in order for it to precipitate, it must be greater than 8.5 times 10 to the power of minus 15. So compare the two magnitude. This is minus 8, this is minus 15. This is a smaller number, right? Meaning to say, if you want your silver iodide to precipitate first, you need a much smaller concentration of silver plus for it to precipitate. Now, because of that, now this is just copied across from the previous slide. So because of this idea, so see, a lower concentration of your silver plus is required to precipitate your AgI. Hence, your AgI will precipitate before your AgCl. Now, move on. Now, question 3A. Okay, this question may sound very scary to you guys, but don't worry, let's break it down together. So you're given in an experiment, excess silver chloride solid was added to 1 dm cube of a solution containing 0.001 mole per dm cube of sodium chloride and is allowed to reach equilibrium at 298 kelvins. So basically means they add it in, they don't just, and after that they leave it to stand or whatever, so that equilibrium can be established first at a constant temperature, the fixed temperature of 298 kelvins. After that, what happened? The mixture was then filtered and the residue was dried thoroughly. Now, when they say filtered, then residue was dried thoroughly, meaning to say what they're trying to tell you here is they give it enough time, for it to drip dry so that you collect all the filtrate, so no filtrate was lost. Basically, that's what they're trying to tell you through this statement here. Now, after that, what happened to this filtrate? 100 cm cube of this filtrate was taken, right? And you need to add 4 times 10 minus 12 moles of your sodium bromide for the first trace of AgBr to appear. Okay, now, given that the solubility of your AgBr in water is this value, calculate the concentration of your silver ions in 100 cm cube of the filtrate. Now, for those of you, if you find that, this entire passage is very scary looking, you cannot visualize what is happening, don't worry. My next few slides, I have some diagram to actually explain to you what happens. So the very first part is this. You see, based on the scenario, right, what happened? I have 1 dm cube of a solution, and this is your your sodium chloride solution of 0.01 mole per dm cube. What you do is you just add in a solid silver chloride excess. You just scoop and add in, and you stir. Let it, stir already. Let it stand. Let it equilibrate. Okay. Now, after that, what do? They do a filtration. Now, because you're adding in excess, right? And don't forget, uh, all halides are all halides are soluble except your silver and your lead halides, right? So see, your silver chloride, you should expect it to be sparingly soluble. So you should expect quite a huge amount here that doesn't dissolve, right? So be it. Okay, so that's why you see we do a filtration. So after you filter, this will be the silver chloride that doesn't dissolve. Now then you have a filtrate here. Now the key thing here is what is now present in this filtrate. What is present in this filtrate will be your silver plus aqueous. Now, this silver plus comes from your AgCl that managed to dissolve, the sparingly soluble one, right? So, sparingly soluble, remember, it means that only a little bit will dissolve. So, this Ag plus comes from that little bit that is able to dissolve. Okay? Of course, you have your Cl minus. Where does this Cl minus come from? Two sources of it. First is because a little bit of your AgCl dissolve, right? So, the little bit that dissolve will contribute to this Cl minus. At the same time, don't forget, you started off with 0.01 mole per dm cube of NaCl solution. So most of it will come from your NaCl. Of course, you also have your Na plus ions present, and this comes from your NaCl, which was the original solution. Okay, so what happens to this then? Now, to this 1 dm cube solution, to this 1 dm cube filtrate, which we have established what is present inside, you actually take out 100 cm cube of the filtrate. And to this 100 cm cube, like what the question told you, you added in 4 times 10 minus 12 mole per dm cube of NaBr solid. This is when the first trace of your silver bromide appears. Now take note, the moment you start to have PPT, it means that the IP will be equals to or greater than the KSP. So the minimum criteria is your IP must be equals to KSP. Okay. Now, with all this entire scenario in mind, now let's work out what the question wants for us. So the first thing you got to do is you can actually calculate the concentration of your bromide ions, because you see this is the amount, right? This is the moles that you use, and you dissolve it in 100 cm cube of the filtrate. That's why you see I can use the amount of the moles here divided by 100 cm cube. I mean, here when I divide by 1000 is to convert it into dm cube. So now you see I realized that in order for my silver bromide to precipitate, the concentration of your bromide ions required will be 4 times 10 to the power minus 11 moles per dm cube. Now, we want to find out about the concentration of silver, right? So, but of course, before that, we need to use the KSP to help us. So the KSP value will be, the KSP expression will be concentration of the silver multiplied by concentration of the bromide ions. So this value has been given to you to be 7.45 times 10 minus 7. You will square it, okay? It will be equals to Ag plus and multiply by the concentration of your bromide ions here. Now, do your manipulation carefully. you will realize that the value, the silver plus concentration will be 0.0139 mole per dm cube. Now at this point, if some of you are thinking, why is it that here I have to square it? Because this value given to you is the solubility value. Don't forget, when you write the KSP expression for this 1:1 ratio, right? It will be x times x, right? That's why it will be x squared. Hence, you see, that's why I have to square the solubility value here. Okay? So now, moving on to 3b, now you're told to calculate the solubility of your silver chloride in water, in your normal water, okay? So see, this is the whole scenario here. Now, in the saturated AgCl, so the KSP will be Ag plus multiplied by your Cl minus, the concentration of each. So this value here, you get 0.01388 multiplied by 0.01388 plus 0.001. Okay, the 0.01 comes from the original value here. All right. So take note, how do I get this value? Because why? Don't forget, the concentration here is the same as the concentration here. Okay? So do everything carefully. The KSP value is 2.065 times 10 minus 4 mole square dm minus 6. So now to find the solubility value, you will just square root this value. So it will be 0.0144 moles per dm cube. Okay, now recall, I mean, this is the same thing I was trying to say in the previous slide. So the KSP expression is Ag plus multiplied by Cl minus, right? So if the solubility is x, so this will be x and x. That's why you see just solubility square. Got it? Okay, now moving on to question 4. Given the scenario here, solubility product, the KSP of your lead sulfate and your strontium sulfate here is these two values respectively. What are the values of the concentration of your lead 2 plus, strontium 2 plus, and sulfate ions in a solution that is saturated with both your lead and your strontium sulfate? So how do we approach this question? Now, I do not know the solubility, right? I mean, I only know the KSP value. I do not know the solubility values. So what I can do, let the unknown be x and y respectively. For the lead, I'll let it be x. For the strontium sulfate, I'll let it be y. Okay, so you can write out the expression. All sulfates are soluble except your ClB and S, right, which is your calcium, lead, barium, and strontium sulfates. So for this case, your lead sulfate is sparingly soluble. That's why you see reversible arrow here. Become Pb2 plus and sulfate ions here. So since well, let it be x at equilibrium, the concentration for your lead will be x. For your sulfate here, take note will be x plus y. Now, why is there the additional plus y here? Because your sulfate, there's two sources of sulfate. One is from the lead, the other is from the strontium. So the sulfate content must come from both, right? That's why I need to add up the two of them together. Now, same idea goes for your strontium sulfate. So you see at equilibrium concentration, the strontium concentration will just have a value of y, but for the sulfate here will be x plus y as well. All right. Now, carrying on from this step, what will happen? So I mean, this is the equilibrium concentration that we established in the previous slide. So what you do now? So I can work out my KSP value. So for my lead sulfate, it will be the concentration of my lead multiplied by my concentration of sulfate. So you see x multiplied by x plus y. And I was given the value is 6.3 times 10 minus 7. I call this equation 1. I mean, by now you should realize, right, that if you have, the moment you have two algebraic terms, you need to solve your simultaneous equation. So similarly, I can do that for my strontium sulfate. So based on the KSP value, I can write out the KSP expression. And now this will be y multiplied by x plus y and is equals to 3.2 times 10 minus 7. I call this equation 2. Okay. Now, I have my equation 1 and equation 2. What I can do now is I can use equation 1 divided by equation 2. When I do that, I mean the x plus y will cancel each other, right? So I will have x in the numerator, y in the denominator. And this value will have 1 divided by the other accordingly. Now do your manipulation of your algebraic terms carefully. You can rewrite this as y equals to 0.5079x. Now I call this equation number 3. So I can now substitute 3 into, 1 or 2, up to you. But for me, my case, I choose to substitute into the first equation. So when I choose to substitute in the first equation and I were to solve my algebraic terms carefully, I will realize that my x value will be 6.464 times 10 to the power of minus 4. Now with this value, now I can substitute into the second equation, or I can substitute into the third equation. So see, in this case, I can work out my y value will be 3.283 times 10 minus 4. Now with these two values now, so see my x and my y value, so now what I can do, now see, so I can now find out my my lead 2 plus will be x, right? The value is x, right? So see, the concentration of lead 2 plus will be 6.46 times 10 minus 4 mole per dm cube. Now this answer is rounded off to 3SF. My strontium is the y value, right? So see, it's 3.28 times 10 minus 4 mole per dm cube. Then for the sulfate, I need to add the two values together. So if I add it up carefully, I will have 9.75 times 10 to the power minus 4 mole per dm cube. So these are the concentrations of the lead, strontium, and sulfate in a saturated solution. Okay. Now the last question of the tutorial, question 5. Very long question, but you see, they started off by giving you this entire scenario first. So these are some general information they want you to be aware of first before you proceed on. So what is the general information you need to know? So they tell you, this question is about your sorts of your group 2 elements. So then these are the following useful information. Sort of group 2 elements with divalent anions, basically your anion must have a charge of -2, tend to be insoluble. When they say divalent anion -2, I mean it's referring to things like, for example, carbonate CO3 2 minus or sulfate SO4 2 minus. So basically, if you have group 2 elements or carbonates of group 2 element, or maybe things like sulfate of group 2 element, I mean these are just two examples, they will be insoluble. That's according to the first point. Okay. Now the salt become insoluble as you go down the group. So basically, as you go down the group, it becomes insoluble. I think this one is straightforward for the second statement. Third statement, salts of group 2 elements with monovalent anion tend to be soluble. So see, group 2 elements, monovalent anions. So monovalent anions will be things like maybe chloride, bromide, or nitrate, NO3 minus, you see the single charge one. So these are the ones that will be soluble, okay? Now, hydrogen carbonates of group 2 elements do not exist in the solid state. So basically, the hydrogen carbonates, let's say for example, magnesium, maybe your magnesium hydrogen carbonate, barium 2 plus, right? So see, barium hydrogen carbonate, they do not exist in solid state. So means gaseous state, liquid state, but I mean aqueous state. So basically, should be your liquid or aqueous state here, lah. Okay. Now, last info. Carbon dioxide reacts with the solution of the carbonate according to the equation. So see, the carbon dioxide in presence of water and the carbonate here, right, it will form an equilibrium, equilibrating reaction. So it becomes 2 hydrogen carbonate. Okay, going forward, going backwards, I mean equilibrium. So now, use the information above and the ideas behind your Le Chatelier's principle. So please recall what your Le Chatelier principle is all about from your topic on chem equilibria. Okay, now, info above, your Le Chatelier's principle and KSP, the concept of KSP, right? Explain your answers for the following questions. Your first question will be your 5A. They tell you, mineral water often contains the chlorides and hydrogen carbonates of group 2 metal. So the solutions of these salts are formed when the rainwater percolates through the rocks of your hills and mountain and emerges as springs in the hillside. Basically, what happens is rainwater seeps through the rocks, okay, seeps through the rock, and in these rocks of all these hills and mountains, they contain all these various minerals, right? They will dissolve inside, and when finally they will emerge as your spring water, and these are the concentration, for one of the spring mineral water, these are the concentration of all the various ions found. Take note, the concentration given to you here are all in grams per dm cube. So first part, calculate the concentration of the ions in mole per dm cube. After that, suggest the formulae of the salt that could exist in the solution and their relative amount. So 3 things to the question. Number 1, concentration in moles per dm cube. Number 2, formulae of the salt. Number 3, relative amount. So 3 things to answer. Let's go for the first one, calculating the concentration in moles per dm cube. So this one I think should be straightforward for you guys. So just use the concentration here, which is given to you in gram per dm cube, divided by the AR of the respective, the AR and the MR of the respective ions accordingly. So for calcium, you'll be 2 times 10 minus 4. Magnesium 2 plus will be 2.02 times 10 minus 4. Chloride will be 2 times 10 minus 4. Then for your hydrogen carbonate, will be 6 times 10 minus 4. Now, look at all the various combinations here. So the combination here, I mean, you have calcium, you have your calcium, magnesium, chloride, and your HCO3 minus, right? So based on the combination, what are the possible? I mean, don't forget, they must be able to dissolve, right, in your water. I mean, and based on whatever, I mean, because you want them to be found in a mineral water, right? then you see based on the information given to you, uh, the monovalent anion, right, of all these group 2, they are all soluble, right? So see, just nice. These two are monovalent as well. So the salt present could be MgCl, MgCl2, CaCl2, MgHCO3 and your calcium HCO3 Okay. Relative amount, we will say is 1133. Now, how do I know 1133? So okay, the main idea here is you compare your chloride and your hydrogen carbonate. You realize in terms of the 10 minus 4, both are the same, right? So it's 2:6. So simplest ratio, 1:3, right? So it's as good as telling you for every 1 mole of whatever chloride you will have about 3 moles of your whatever hydrogen carbonate. So see for the magnesium chloride to magnesium carbonate here, there's a magnesium hydrogen carbonate, right? See, 1:3. For the chloride also, for the calcium version, also 1:3. Okay, now this question itself, there are many possible answers. Okay, so as long as you take a look at the footnote I wrote here I highlight in blue here. So see, several equally correct possibilities are accepted as long as the ionic ratio calculated. Basically, when I check your Mg2 plus to calcium 2 plus must be a 1:1, your your chloride ions to HCO3 minus must be 1:3 is met. As long as you meet this criteria, all the possible, there's a lot of possibility we can accept. Okay, of course, there will be a better answer. There will be one better answer compared to the rest. So the better answer here will be only a combination of one chloride and both hydrogen carbonates. Now, why do I say so? Because why? If you continue on the question, right, if you read the full question before your attempt, you will realize that they actually tell you that there is only one salt remain when the water was partially evaporated. So this is a hint to you. You only have one salt left, so that's why you should only have this one. Okay. Now moving on. Now in 5b, right? So you see you're told about this scenario. Sample of the mineral water was partially evaporated. A mixture of white solids was formed. Solution containing a single salt remained. So suggest the identity of the first solid to be precipitated. Explain your answer. So based on the previous part, our proposal is magnesium and calcium chloride, magnesium and calcium hydrogen carbonate. So my suggestion here, our suggested answer here is calcium carbonate is the first salt to be precipitated. Now why? Your calcium carbonate is less soluble than your magnesium carbonate. Why? Based on based on the general info given, they tell you as you go down the group, it becomes less soluble. So your calcium is below your magnesium, right? So because of that, I will expect the calcium carbonate to be less soluble. And if it's less soluble, it should be the one to precipitate faster as well. Okay, so you see based on that info, because I know that it's less soluble, I will say that the KSP value will also be lower than that of your magnesium carbonate. Now, so how does this, the scenario given to you is about the partial evaporation. So how does the partial evaporation helps, or causes this precipitation to occur? When you have the partial evaporation, what will happen is you cause the CO2 to be lost or to be removed from the solution. Okay, so you reduce, right? So what happened now? When your CO2 is lost or removed, right, based on this equilibrium given to you in the general info, uh, your position of equilibrium will shift towards the left-hand side, or you favor the backwards reaction. Now, when this happens, there will be an increase in the concentration of your CO3 2 minus. Now, what happens now? With this increase in the CO3 2 minus, the IP, right, will cause the IP of your calcium carbonate to be higher than the KSP of it. So while the ionic product of your magnesium carbonate, right, it will still be lower. Hence, your calcium carbonate will be the first one to be precipitated. So basically, what this entire this entire paragraph here is trying to tell you is that because of the increase of your calcium carbonate, both your IP for your calcium and your magnesium carbonate will be affected. They will be high. They'll increase. But because you see your KSP of your calcium carbonate is already a smaller value, when you increase, right, you will tend to be able to exceed this smaller value more easily. That's why calcium carbonate will precipitate first. But for the magnesium carbonate, the value is a slightly larger number, right? So it's harder to exceed. That's why harder to exceed, you will not precipitate first. Okay. Now 5C. So suggest the composition of the so the last question here, 5C, suggest the composition of the rocks through which the rainwater had perchlorated, and explain how the mineral water has been formed. Suggest, okay, so maybe, so what we suggest here, or what we think is that, maybe the rocks of the hills and the mountains contain your carbonate, your magnesium and calcium carbonate, as well as your magnesium and your calcium chloride. So what will happen? Your amphoteric carbon dioxide dissolve in the rainwater. Don't forget, in our air we have carbon dioxide, right? They will dissolve in our rainwater. So the carbon dioxide that dissolve in the rainwater will react with the CO3 minus formed from the partial dissolution of the sparingly soluble calcium carbonate and your magnesium carbonate. So remember this equation given to you. So because these two are sparingly soluble, so you have part of it. So what will happen? It will interact with your carbon dioxide. You see, this one comes from the salt. This one comes from the carbon dioxide in the air. So because of this, it will interact. You will shift the POE towards, you will shift the position of equilibrium POE towards the right hand side. So you form more and more of this. So when you form more and more, so when you form this, I mean the concentration of this will drop, right? When the concentration of your carbonate drop, I mean according to LCP, when the concentration of this drop, the system will want to replenish this, right? How will they replenish this? The only way to replenish this is to cause more and more of your magnesium and calcium carbonate to dissolve, to replenish this. Okay? Now, then as for your MgCl2 and CaCl2, right, both of them are soluble. How do I know that they are soluble? The general info given to you, the monovalent anion of group 2 elements, right, are soluble. So see, Cl minus, they are monovalent. So see, since both of them are already soluble, they will dissolve to give you Mg2 plus, Ca2 plus, and Cl minus. So that is how I account for the presence of these ions in the solution. Okay. Now, the last question here I know is a bit tougher, is its application in some unknown or novel context. So please take some time to listen through this debrief again to try to figure out what is happening. Of course, if you still have problem, please feel free to approach any of the tutors here. We'll be more than happy to explain to you again. Okay. Now that is the end of this tutorial debrief for the topic on solubility equilibria. Okay, thank you.